Hi class, in this lecture here we're going to move into section 2.2, and this is going to be about using the second derivative to find maximum and minimum values in sketch graphs. So if you remember in what we used in section 2.1, we used the first derivative f prime of x here. Okay, we used it to find increasing and decreasing intervals, and also to help us find relative extrema. So we're gonna in this lecture here we're gonna be talking about second derivatives. Okay, so f double prime of x, and we'll talk about something about how you use the second derivative to find maximum minimum values. Excuse me, and then what we'll do is we'll talk about what the application to the second derivative is, something called concavity. All right, so to start, let's start with what I was talking about with concavity. So there are two types of concavity in our class. There's what's called concave upward or concave up, and then there's what's called concave downward or concave down. All right, so it goes like this. Suppose that f is a function whose derivative f prime exists. All right, and this f prime exists at every point in some open interval. Then the function f is concave up on that interval if f prime is increasing. Well, how can you determine if f prime is increasing? Well, you look at the rate of change at f prime. Well, what's the rate of change of f prime? Well, that's f double prime, right? And so look, here's what it means to be concave up. It means the slope of the tangent line is increasing. So if you look here, what we're saying here is this graph is concave upward from the interval from A to B. And if you look here, look what's happened to the tangent line. It's sloping downward, and then the tangent line, is slowly turning, and the slope of the tangent line is increasing. Okay, that's what's going on. Like the curve is bending upward. F is concave downward on some interval I if f prime is decreasing over that interval. So what's going on here when we say concave downward is the slope of tangent line is decreasing. And look, if you look here, here's the tangent line, and then from A to B, this tangent line, the slope, look, from here the slope is positive, and then look, the slope of the tangent line is negative. So the slope of the tangent line is decreasing, it's going down. Okay, so the rate of change here of the first derivative is decreasing, and for concave downward and for concave upward, the rate of change of the first derivative is increasing. So what we can do to find a test of concavity, then, it's a lot like the first derivative test here from the previous section, or we use the sign of the first derivative, to find intervals for increasing and decreasing. We can use the sign of the second derivative to figure out if what intervals the graph is concave upward or downward. So if f double prime of x is greater than 0 on an interval I, then the graph of f is concave upward. Okay, so f prime is increasing, so f is turning up on the interval. So this is just like what we're going to do when we find the intervals for increasing and decreasing. Okay, we're going to find an interval. We're going to pick a test value in the interval. And then if f double prime of test value is positive, so greater than 0, it's concave upward on that interval. And I'm going to do an example of all this. And then the flip side, if f double prime of x is less than 0 on interval I, then the graph of f is concave downward. All right, that means the derivative, the slope of the tangent line, is decreasing, and the graph, the function f, is turning down on that interval. So we're going to do the same thing. All right, we're going to find an interval, and I'll show you how to do that. We're going to pick a test value. in that interval. And then if f double prime of that test value is less than 0, okay, then it's concave downward on that interval. All right, this leads us to what's called the second derivative test for finding relative extrema. So you can actually use the second derivative to determine if you have a relative max or min. Instead of looking at like, is it increasing, changing from increasing to decreasing, we have a relative max, or decreasing, increasing, we have a relative min. The second derivative actually tells us. All right, so suppose that f is differentiable on every x in an open interval a to b, and that there's some critical value c in that interval for which f prime, so the first derivative, is equal to 0. Okay, so what we're saying here is we have a critical value at x is equal to c. Okay, so this works a little bit differently than you would think. Okay, so f prime of c is a relative min if you take the value of c, the critical value, and plug it into the second derivative and it's positive. Okay, so if f double prime of c is greater than 0, it's a relative min. Boom. If f double prime of c, or excuse me, f of c is a relative max, if f double prime of c is less than 0. So if you take c and plug it into the second derivative and the value is negative, you have a relative max. If you take this critical value and plug it in and you get the value equal to 0, then what you can do is you can just use the first derivative to determine whether f of c is relative extreme. And this second derivative test fails, so you'll have to use another method. All right, one final thing here, and then what we'll do is we'll work an example. Points of inflection. So points of inflection occur when you change from being concave downward to concave upward, or from concave upward to concave downward. So if f is a point of inflection in a graph, it must occur at some point x sub 0 in the domain of f, where when you plug it into the second derivative, it's equal to 0, or f double prime of that value does not exist. Then x0 comma f of x sub 0 is a point of inflection. Okay. So let's, now that we have the second derivative, we have this concave upward, concave downward, these points of inflection, let's do an example. So you're given this function, okay, so just some polynomial third degree function. So f of x is equal to x cubed plus 3x squared minus 9x minus 13. And here's what I want to do. I want to find the first and second derivatives. I want to identify relative extrema. I want to find the intervals of the function is concave upward and concave downward. And then I want to find the points of inflection. Okay. So let's do this. All right, so let's find the first and second derivative. So let me just rewrite the function on the next slide here. So our function, f of x, was equal to x cubed plus 3x squared minus 9x minus 13. So the first derivative, okay, f prime of x is equal to, bring the 3 down, so 3x squared plus bring the 2 down, 6x. This is just minus 9. Great. And the second derivative, just the derivative of the first derivative, bring this down. So we get 6x plus 6, and then the derivative of 9 is 0. So here's the first and second derivatives. Okay? We got those. Next question says, identify the relative extrema. So what I'm going to do is I'm going to find the critical values, and then I'm going to use this second derivative test for relative extrema. Okay, so to do that, again, first thing you need to do is you need to find critical values. So you're going to look at your first derivative, f prime of x. That was equal to 3x squared plus 6x minus 9. And you're just going to look where this equals 0. So you're going to have to solve by factoring. So you factor out a 3, and you get x squared plus 2x minus 3 is equal to 0. This trinomial will factor, right? So it'll factor into x plus 3, x minus 1 is equal to 0. So it looks like you have critical values here, right? Just using, the 0 multiplication property here. So either x plus 3 is equal to 0, so you have a critical value at x is equal to negative 3. And you have another critical value at x is equal to 1, right? When you set x minus 1 equal to 0. So what we're now going to do is we're going to use the second derivative test to identify extrema. So you're going to look at the second derivative, right? So looking back, f double prime of x, the second derivative, was 6x plus 6. Well, look, here's what you can do. You're going to take these critical values, okay, and you're just going to plug them right into the function, okay? So f double prime of 1, well, when you plug that in, you get 6 times 1 plus 6. What is that? That's 12. That's greater than 0, right? So now look, if the sign of the second derivative at the critical value is positive, you have a relative min, okay? So we have a relative min at this point 1 comma f of 1, which is the point 1 comma. So you would take 1 and you would plug it back into this function, okay? And when you do, you end up getting minus 18. So now let's do the same thing with this, okay? So you're going to take the value of negative 3 and plug it into the second derivative, right? So this is minus 18 plus 6 gets me minus 12, which is less than 0. So the sign of the second derivative evaluated at this critical value is negative. It's less than 0. So you found a relative maximum because the second derivative evaluated at the critical value is less than 0. Boom, relative maximum. So we have a relative max at this point, negative 3 comma f of negative 3. And just to save a little time, when you plug negative 3 into the original function, you get the value 14. So we've got it. We've got the relative min of the function, and we've got the relative max of the function. All right, so the next thing you're going to do is you're going to look at intervals where the function is concave upward or concave downward. All right, so to do that, okay, what you first need to find, so this is intervals of concavity. You need to look where f double prime of x, which was 6x plus 6, where this is equal to 0, okay? And just solving this, right? You subtract 6 over, you divide by 6, and you get x is equal to negative 1. So you're going to set up a table just like we did for intervals of increasing or decreasing. All right, so you're going to think of the whole number line. You're going to go from negative infinity till you get to negative 1. And then you're going to go from negative 1 to infinity. You're going to pick a test value. So pick something easy, right? So what's an easy number in here? You're going to pick negative 2. What's an easy number between negative 1 and infinity? You're going to pick 0. And then look, I have my intervals. The interval I. So now we're going to look at the sign of the second derivative with that test value. So you're going to look at the sign of the second derivative evaluated at that test interval. So f double prime of negative 2. Well, look, if you plug negative 2 in here, Okay, negative 2 times 6 gets me negative 12, plus 6 gets me negative 6. So that's less than 0. So what this tells me, when the sign of the second derivative is negative, it's concave down on this interval. Now I'm going to take my test value and plug it in to the second derivative. Well, 6 times 0 is 0, plus 6 is 6, which is greater than 0. So the sign of the second derivative is positive. So now this is concave up on this interval. All right, so what I'm going to do is I'm going to break this lecture up into a second video. So I'm going to record another lecture that goes into a much deeper example that works about sketching graphs, and finding increasing, decreasing relative extrema, concavity, points of inflection, and everything from there. And let me go back one last quick thing before I do that. Points of inflection here. Sorry about that. Point of inflection, my apologies. Point of inflection occurs where this derivative, or the second derivative, is equal to 0. So it occurs at the point -1 f of -1. And what you have to do to figure out that is you just have to plug -1 into this function. So you would get -1 plus 3 plus 9 minus 13. So if you look here, what does this get? So this gets me 2 plus 9 minus 13. So 11 minus 13 gets me minus 2. So the point of inflection occurs at this point, -1 minus 2. Sorry for skipping ahead there. So as I was saying, what I'm going to do next, I'm going to break this up, and I'm going to do a real long example where as you can see, I'm giving a little bit of a preview. I take this function and I'm going to do all of this for you. So that'll be coming up in the next lecture.